Guys, welcome to Send the Mix online tutorials. On today's episode, we'll be discussing on the source-free RL circuit. Welcome back. So now, in the previous video, we made an introduction to what an RL circuit and what an RC circuit is, or what it entails, and we discussed on how to solve a circuit of a source-free order. So in this video, we'll be discussing on the RL circuit in the source-free section. So now the key to working with the source-free RL circuit is to find what the initial current IO through that inductor and the time constant T of the circuit. You know, in the previous video when we were discussing on RC circuit, we said that the key to working with that is to find the voltage VO, the initial voltage, VO, and we also said finding the time constant T. But in the case of RL, we are going to find the initial current IO through that inductor. Now the time constant for the RL circuit is equal to, now the time constant T for the RL circuit is equal to L over R, which is the inductor over the resistance. But for the capacitance, the T equals to CR. Do you understand it now? Now, if you've not been following, I suggest you pause this video now or you stop the video and go and watch the video on the RC so that you can understand it from step to step. So that with that being said, now let us check for current in respect to time. We say it is I naught exponential minus T over, is still the same with that of the capacitance, but in this case current, initial current, that's it. So let us solve an example to understand this point and drive it home the more. So now, assuming that the I naught is equal to 10 ampere, the question says calculate IT and IX in respect to T in the circuit. Now let me draw the circuit so we can all see it. As you all know, this is not the standard to represent it, so we have to represent this circuit in you know what this triangle, this one is an independent variable. Do you understand what I mean? This one is an independent variable. Now this one is 0.5 Henry, and this is I coming down to that point, and this is IX also coming down to the point. This is 4 ohms. So that is that for that. So now we need to obtain the equivalent resistance at the inductor terminals and then use this formula. As I said, this formula, we need to find we need to obtain the equivalent resistance at the inductor terminal and use this formula. So now, what we're going to do now, we're going to apply Kirchhoff voltage law to the two loops, because we now have a loop 1 and a loop 2. So we have to apply Kirchhoff voltage to know the current or the voltage in this case that is coming into this circuit, or into this stuff we draw here. So now let me draw the circuit again. Let me draw the circuit here. Let's say this is our terminal A and what? And B. This is the 4 ohms. This is I naught tending towards E, and this is B. This is the voltage, the dependent voltage, V naught is equals to 1 volt. See, it was not given in the in the previous in the representation. This is loop 1, this is loop 2, but the current I1. Let me write it. Let me represent it as current I1. Now this current here is what we call mesh current. It is not the same current as the current that's flowing in. Those are the current we use to identify what is happening in this circuit. So now let us solve. So now we have, so when we represent this in mesh, remember, let us get for the loop, for the first loop we have 2. Let me be specific so that we'll not run into trouble here. This is 2. Remember the video we have made on resolution of this stuff. We say it is going to be this I1 minus what, the I2, because they share the same current. So you say 2 open bracket I1 minus what, I2. After that you come to this part. Is there any resistance there? No. So you come here. Is there any resistance here? Yes. Voltage is equal to 1. So you say, but look, it is going to the negative. Can you see what is happening here? It is passing through the negative terminal. But once you are calculating for the voltage, if it passes through the negative terminal, it's going to be considered as a positive. But if it passes through, it goes up or come to this positive, it's going to be considered as a negative. So in this case, it's coming down into negative, so it's going to be considered as a what? Positive. It is equal to 0. So our I1 minus our I2 will give us half. If this come here, it becomes minus 1 divided by 2. So that's how that happened. Now for the loop 2, yes, look at it. Now for the loop 2 now we'll then begin from, that's where we're going to begin from. So let us begin from this place. Let's start there. So we have our positive 4 is coming this way. Our positive 4I, because this is the I2. It is flowing in with I2. Come this way. Now this one is going to be 2. So it's going to be I2 now minus what? I1. This was happening now. It's now going to be plus 2 I2 minus what? I1. After that, then you then come to this part, which is now it is going to the positive, so it's going to be considered as what? Negative. It's what I was talking about there. So it's going to be now negative 3I1. Now solving that, you'll be having 6I2 minus 3I1 minus 2I1, which gives us 0. So our I2 will now be equal to 5 over 6I1. So now when we substitute this, let us say this is equation 2 and this is equation 1. Let us substitute equation 2 into equation 1. This is what we're going to have. I1 is going to be equal to minus 3 ampere. So now when we've gotten our I1, we now need to calculate our equivalent resistance. And our equivalent resistance is also what is also called thevenin's resistance. So our equivalent resistance flowing in this circuit, because after we've gotten our I1, which is equal to, is now equal to 3A minus 3A. Now look at our, can you get the part where we get our minus 3A from? Remember I said your I2 is this, right? So now when you input this I2 now in this place, you solve your answers to get your I1. Hope you are following me. Maybe you can pause the video and try that out. There's not much time for us to keep on doing that. So now we need to get our resistance, our equivalent resistance, which is equal to V naught over I naught, which gives us 1 over what? 3. Which is now equal to ohms. No. I'm sorry, ohms. So not ohms. So now, if that has been gotten, now we need to get our time constant. Remember I said our time constant. Are you seeing that? I'm sure they. Time constant T is equal to L over what? R. Which gives us, what is our L in this case? Our L is what? where's our L is, oh, we've cleaned it. Our L is 0.5 over our resistance. This is equivalence resistance. You see now where it is being needed. Can you now understand what is happening here now? It is equal to 1 over 3, which gives us 3 divided by 2. One side going to be 3 over 2 seconds. So now we will see, let us calculate our current through the inductor. Current through the inductor in time t will now be equal to I naught exponential minus t over time constant, which is equal to 10 exponential minus t, which is what we don't know at this point. But we now as our time constant to be 3 over 2. So it's going to be 1 over 3 over 2, which will give us, let me just put it here. Now 3 over 2, when you get the inverse of it, it becomes 2 over 3 times. I'm going to be in what? Ampere. So our I t is equal to that. And remember, our t is greater than what? 0, because that's only when this can stand. Once this is equal to 0, our e raised to the power 0 will just be equal to what? 1, and thereby turn our it to just become 10. So our t in this case will be higher than what? 0. Now I'm going to be dropping a comprehension, but before that, let me draw the. Well, I don't know what I'll make it as a picture. I'll make it as a picture, then I'll post it, so you can solve the comprehension there and drop your answers on the WhatsApp platform that we converge. If you don't have the link to the WhatsApp platform, I'll be dropping it in the description link below, so you can join on. And that's it. So bye bye.